So we have this PV diagram, and the gas expands from 4 liters to 12 liters. It's going from point A to point B at a constant pressure of 5 atm. How much work is done by the gas in joules? Now the first thing we need to know is what kind of process we're dealing with. Because the pressure is constant, we are dealing with an isobaric process. Think of a barometer that's associated with pressure. Iso means the same, so the pressure is constant. It doesn't change in this example. And to calculate the work performed by the gas is going to equal the pressure times the change in volume. So the pressure is 5 atm. The final volume is 12 liters minus the initial volume of 4 liters. So 12 minus 4 is 8. 8 times 5 is 40. So the work is 40 liters times atm. Now we need to convert that to joules. So 1 liter times 1 atm is 101.3 joules. So that's the conversion factor that you need. So it's 40 times 101.3. And so the final answer for this problem is 4,052 joules. And that's it. Now it's important to understand that the work done in a PV diagram is the area under the curve. And so the area is length times width. In this case, the length represents the change in volume, and the width is the pressure. And so that's where you can get this equation. So the area is just the pressure times the change in volume. So make sure you understand that. To calculate the work done from any PV diagram, all you need to do is find the area under the curve. Number 2, the pressure of a gas inside a rigid 5-liter container changes from 4 atm to 2 atm. So how much work is performed during this process? So notice that the volume of this rigid container is fixed. So the volume is constant. Therefore, we have an isovolumetric, also known as an isochoric process. In this case, the change in volume is 0. So notice that there's no shaded area or shaded region that you can draw in this diagram. For an isochoric process, the work will always be equal to 0 because the change in volume is 0. And work is really the integration of the pressure times the change in volume. So if the change in volume is 0, then the work is going to be 0. So this is always true for any isochoric process. W is always equal to 0, so keep that in mind. Number 3, 5 moles of nitrogen gas expands at a constant temperature of 400 Kelvin from 3 liters at 6 atm to 9 liters at 2 atm. How much work is performed by the gas? So this time the temperature is constant. So what we have is an isothermal process. The change in temperature is 0. And to calculate the work performed for an isothermal process, once again, it's the area under the curve. Now it's not easy to calculate the area under the curve in this example. Fortunately, there's a formula that can help you to do so. It's nRT, natural log, of the final volume divided by the initial volume. So N in this example is 5 moles, R is 8.3145 joules per mole per Kelvin, and the temperature is 400 Kelvin. And then it's the natural log of the final volume, which is 9 liters, divided by the initial volume of 3 liters. So it's going to be 5 times 8.3145 times 400 times the natural log of 3. And 9 divided by 3 is 3. And so W is going to be 18,269 joules. And so that's it for this problem. Number 4. Argon gas expands adiabatically from 0.01 cubic meters at 20 times 10 to the 5 pascals to 0.03 cubic meters at 4 times 10 to the 5 pascals. How much work is done by the gas? For an adiabatic process, the heat transferred is zero, but we don't have to worry about that in this example. To calculate the work, the formula that we need is negative CV over R times the final pressure multiplied by the final volume minus the initial pressure times the initial volume. Now we have a monoatomic gas, and CV for a monoatomic gas is 3 over 2 R. And so if we replace CV with 3 over 2 R, we could cancel R. So for this particular example, W is going to be negative 3 over 2 R times the product of the pressure and volume minus the initial pressure and volume. So that's going to be negative 3 over 2 times 8 point, well, that R should not be there anymore. I don't know why I wrote it again. So it's negative 3 over 2 times the final pressure, which is at point B, that's 4 times 10 to the 5, multiplied by the final volume of 0.03 cubic meters, and then at point A, the initial pressure is 20 times 10 to the 5, and the initial volume is 0.01 cubic meters. So go ahead and type that in. I'm going to do it one step at a time. So first, 4 times 10 to the 5 times 0.03, that's 12,000. And then 20 times 10 to the 5 times 0.01 is 20,000. So 12,000 minus 20,000 multiplied by negative 3 over 2, this is equal to positive 12,000 joules. And the work should be positive for any type of expansion process. So that's it for this problem. Number 5. How much work is performed per cycle as the system moves from A to B to C to D to A? So from A to B, let's go in that direction, and then B to C, C to D, D to A. Now to calculate the work performed, it's simply the area that's enclosed by the PV diagram, especially if you have a cyclic process. So the area is simply length times width. In this case, the length is basically the change in volume, and the width is the change in pressure. So you could say it's delta P times delta V for this example. So the difference in pressure, 8 times 10 to the 5 minus 2 times 10 to the 5, that's the difference of 6 times 10 to the 5 pascals. And the change in volume, 0.08 minus 0.02, that's 0.06 cubic meters. So it's 6 times 10 to the 5 times 0.06. And so the answer is 36,000 joules. Now, should this answer be positive or should it be negative? It has to do with the direction of rotation. Notice that the system is moving in the clockwise direction. So if it's moving in the clockwise direction, the work performed per cycle is positive. If it's moving in a counterclockwise direction, so let's say if it's going in this direction, the work performed per cycle will be negative. So for this example, it should be positive since it's moving clockwise. Now we're going to confirm this answer by calculating the work for every step. So what's the work performed going from A to B? From A to B, we have an isochoric process. The volume is constant. It's 0.02. It doesn't change. So it's 0 going from A to B, and also going from C to D. Whenever you have a vertical line, the work is going to be 0. Now from B to C, we have an isobaric process because the pressure is constant. And so we could use this formula. It's going to be P times delta V. So the pressure is 8 times 10 to the 5. And as we go from B to C, the final volume is 0.08. The initial volume is 0.02. So this is going to be positive. 0.08 minus 0.02 is 0.06 times 8 times 10 to the 5. So that's equal to 48,000 joules. So we're going to have to add up these values. But before we do that, let's calculate the work that's performed going from D to A. So the pressure at that point is 2 times 10 to the 5. And the change in volume, the final volume from D to A, is 0.02. The initial volume is at point D, that's 0.08. So 0.02 minus 0.08, that's negative 0.06 times 2 times 10 to the 5. So this is going to be negative 12,000. So what we need to do is add up all the values highlighted in green. So that's going to be positive 48,000 plus negative 12,000, and that's going to give us this answer, 36,000 joules per cycle. So for one whole cycle, the gas will perform 36,000 joules of work. So now what about in 50 cycles? So if it's 36,000 joules for just one cycle, then all we need to do is multiply it for 50 cycles. So 36,000 times 50, that's going to be 1.8 million. Or 1.8 times 10 to the 6. So that's how much joules of energy or joules of work that's going to be performed over the course of 50 cycles. Now let's work on this problem. So our goal is to calculate the work performed as the system moves from A to B, and then B to C, and then C to A. So from A to B, it's moving there at constant pressure. So the work to go from A to B, that's going to be P delta V. And so the pressure is 2 times 10 to the 5 pascals. And then the change in volume is going to be the final volume, which is 0.01, minus the initial volume of 0.10. So that's going to be negative 18,000 joules. Now, going from B to C, we have an isochoric process. So because the change in volume is 0, the work is going to be 0 for that process. Now, from C to A, it expands isothermally. So therefore, we can use this equation, nRT times ln V final divided by V initial. And one thing I forgot to do is give you the number of moles of gas. So let's say the number of moles is 5. That's not going to affect this answer. Or actually, you know what? We can calculate the number of moles. So it turns out that I really didn't need to give you it. So we can use this equation, PV is equal to nRT. Now the pressure we need to choose a point. So going from C to A, the temperature is held constant. So we can use point C or point A. I'm going to use point C. So at point C, the pressure is 20 times 10 to the 5 pascals. And the volume is 0.01 cubic meters. Our goal is to calculate N, and R is going to be 8.3145 if the pressure is in pascals and if the volume is in cubic meters. And the temperature is 400 Kelvin. So it's going to be 20 times 10 to the 5 multiplied by 0.01. That's 20,000. Divide that by 400, and then divide that by 8.3145. So N is 6.014 moles. So now we could use this formula to calculate the work, going from C to A. So it's going to be N, which is 6.014, times R, that's 8.3145, multiplied by the temperature, which is 400 Kelvin in this example, and then times ln. Now going from C to A, the volume changes from 0.01 to 0.10. So the final volume is 0.10, and the initial volume is 0.01. So go ahead and type this in. So this is going to equal 46,055 joules. So the total work is going to be the sum of these three highlighted values. So it's going to be negative 18,000 plus 46,055. So that's going to be positive 28,055 joules. So that's the answer. And we can see why the net work done is positive. As we mentioned before, the system is moving in this direction, in the clockwise direction. If it was going counterclockwise, the net work done would be negative as opposed to positive. Number 7, how much work is performed as the system moves from A to B to C and back to A? So for a cyclic process, we just got to find the area enclosed by this PV diagram. So we have a shape of a triangle, and the area of a right triangle is 1/2 base times height. The base is the change in volume. So the change in volume, 0.10 minus 0.02, that's 0.08. And the height is basically the difference in pressure. So 8 minus 2, that's going to be 6. Half of 0.08 is 0.04 times 6 times 10 to the 5. So the work is going to be 24,000 joules. Now, is the cycle clockwise or counterclockwise? Notice that it's going in this general direction. So that's counterclockwise. Therefore, the work done should be negative as opposed to positive. So the work done per cycle is negative 24,000 joules. Now let's confirm this answer by calculating the work done for every segment. So let's start with A to B. Going from A to B, that's an isobaric process. So it's simply pressure times the change in volume. So the pressure is 2 times 10 to the 5 pascals. The change in volume is going to be the final volume, 0.10, minus the initial volume of 0.02. So 0.10 minus 0.02, that's 0.08 times 2 times 10 to the 5. So this is going to be positive 16,000 joules. Now let's calculate the work going from B to C. So that's an isochoric process. The volume doesn't change. So the work there is going to be 0. Now what about going from C to A? What can we do? In going from C to A, notice that it's a straight line. The volume is changing and the pressure is changing. So it's going to be very similar to this equation, but it's going to be an average pressure. So it's going to be 1/2 times the initial plus the final pressure multiplied by the change in volume. So the initial pressure going from C to A, that's 8 times 10 to the 5. The final pressure at A is going to be 2 times 10 to the 5. And the change in volume, the final volume is 0.02. The initial volume is 0.10. Let's see if I can fit that here. So 8 plus 2 is 10. 1/2 of 10 is 5. So the average pressure between C and A, the average between 2 and 8 is 5. So the average pressure is 5 times 10 to the 5 pascals. And then the change in volume, 0.02 minus 0.10, that's negative 0.08. And so this works out to be negative 40,000 joules. So now we can add up the values. So 0 plus 16,000 plus negative 40,000 will give us negative 24,000. So we can see that for a cyclic process that's going in a counterclockwise direction, the work is indeed negative. If it's going in a clockwise direction, the work performed by the system or by the gas is going to be positive.